Good morning, everyone. Today we will start with an interesting topic which is called measure theory. This is an introduction, the first lecture of measure theory. So let's get into it. First, measure theory, it's like a continuation from set theory. So we have set theory here, and then we go into measure theory. So the difference with set theory is that we will use all of the operations of set theory, like the union and the intersection and so on, but now we will associate some functions, some other structure to these sets. So we will have a set here and then some structure associated with this set, and then even we will associate some functions with these sets. And so this is an extra structure that will provide a set that is here with some characteristics or some properties that are of our interest. So for this, to understand measure theory, it's required that you are proficient with set theory, at least at some basic level or some bachelor level. So getting into it, we start with a definition. Let's go with this definition. Number 1. All right. So let's start with a set that we label as X that is different from 0. And let's say we have some collection that we label as some collection of subsets of the set X. We'll say that this collection is called a sigma-algebra of X if and only if it holds the following 3 properties. The first is that X should be included in the sigma algebra. The second is that for every pair of elements in the sigma algebra, the difference between A and V is also an element of the sigma algebra. And the third property is that if you have a family, a countable family, let's say like this, in the sigma algebra, then the countable union of all of these sets is also an element of the sigma algebra. So with this definition, we say that if you have a set, let's say X, and its sigma algebra, then we say that the elements of A, let's say A in the set, is a measurable set. And this pair here is called a measurable space. So this here is the sigma algebra of X. Now, if you downgrade this property here into not countable unions but finite unions, let's say if you have a finite family, let's say from K1 into Km, and it always holds a countable family in the set A, and this implies that the finite union of all of these sets is also an element of the set. Then if the property 1 and 2 also hold, then this new property will imply that A is an algebra. So we say that it is a sigma algebra when you can do this not only for finite sets, for finite families, but also for countable family, which could be, of course, countable in finite families. So we can make some small proposition here. Let's say proposition 1, that every sigma algebra is an algebra. So it is obvious that if some set is a sigma algebra of X, then 1 and 2 also are all the same for algebras. Then we only needed to prove that this implies that our third property implies the third property of algebras. So to do this, of course, we start with some finite family in our sigma algebra. Then we need to complete it, or to turn this finite family into a countable infinite family. So we need to append some elements of the sigma algebra. But of course, we want to show that this finite union is an element of the sigma algebra, and this will make the sigma algebra an algebra. So to do this, we need to, we want to prove this finite union, but we can only have infinite unions. Then we need to complete this into some infinite family. The obvious choice will be to start with the same elements, the same m elements, and then append the empty set an infinite number of times. But to do this, we will need to have for granted that the empty set is an element of the sigma algebra. But this follows because you know that the whole set, let's say the whole space, we can call this element the space, because it is our like our universe of reference. So this space is an element of A, but by the property 2 we will have the space minus the space, because since the space is an element here, then the space minus the space, which is the empty set, should be an element of the sigma algebra. Since this is an element of the sigma algebra, you can use it here to append and turn this finite family into an countable family. And then you will have that the desired property. So this is equal to this, because from m into the infinity, it's always the empty set, so that this is the same, and this will be an element of the sigma algebra, and then this makes the sigma algebra an algebra. So it's kind of trivial. And now we continue with some examples. Let's make here a quick example number 1. So we have an set that is not empty, then the empty set together with the set is a sigma algebra of X. Well, why? Because it holds that the space is an element of A, and for every pair of elements, its difference is in A, of course. The only combinations are this, and this. And this is the empty, which is an element. This is also the empty. This is also the empty, and this is X. So for every difference, the result is always an element of A. And then for countable families of elements, you can only have families with the repetitions of the empty set or the whole space. And if the whole space is an element of the family, then the union will of course be the space, and this is an element of the set A. And if the family only have empty sets, then its countable union will be the empty set also, and this is also an element of A. So this is a sigma algebra. It's kind of trivial, but this is an example of a sigma algebra. So this is the smallest. Let's highlight this as the smallest sigma algebra that you can define on a set, on any empty set. Set that is different from the empty set. So we have another example. So another trivial example is the power set of X. Let's write it here, example number 2. If you have a set that is different from the empty set, and why I'm writing this time and time again, this condition, because this is by definition. This sigma algebra is only defined when the space is different from the empty set. So this was a typo. It's different from the empty set. So if you have a non-empty set, then sigma algebra on this set is the set of parts of X. So this is also a sigma algebra of X. And why is that? Well, because of course in the power set of X is an element of the power set, so the first property is met. Then for every difference of elements of the power set, its different is also a subset of X, so this is an element of the power set, and so the second property is met. And then if you have a family of subsets of subset of X, let's write it like this, where it's a subset of X, then its union, its countable union, will also be a subset of X, which then this implies that this union it's an element of the power set, which is our set A. So this means that the power set is a sigma algebra of X. So this is, let's say, the biggest sigma algebra. So the smallest is the sigma algebra composed of these two elements, the space and the empty set, and the biggest is the sigma algebra that is composed by all of the power set. So both are trivial sigma algebras. Now let's continue with a third example. So what happens if you have a non-empty set, and let's say we have we pick a certain subset of X that is different from the empty set. Of course, this can be the whole space, but it may be a proper subset. It doesn't matter. Then we can define an algebra here. Of course, the empty set is always there. Then we have A. Then these two sets. This is the complement of X, which is of A, which is X minus A. So this is also a sigma algebra. And why is that? Well, because, well, the first property is met since X, the whole space, is an element of A. And then when you make difference from all of these, from these four elements, the difference is always an element of A. We can show that pretty quickly. Well, from the empty set and the space, it's obvious that by the first example that the difference is in A. And then what happens when you make the difference between A and its complement, and this is the empty set, and the other side is also the same. And what happens when you make the difference between X and its complement, then the difference is A, and the difference between this is the complement. So this is pretty much everything. So yeah, the second property is also met. And then for the third property, the union, well, you only have 4 elements. So if in the family you have A and the complement of A, then its union, whatever else there is, it will be the whole space X, the union. If you have X as an element, then its union will be X. If everything is the empty set, it will be the empty set, and so on. So it's kind of also obvious that countable unions are always in the set A. So this makes it a sigma algebra. So this is our third example, and this is also the smallest. But this is not the smallest algebra that is in X, but the smallest sigma algebra that contains A. Of course, if A is X, then this will be equal to this, and this will be equal to this. So the smallest sigma algebra that contains a subset of X, it's always a set with 2 or 4 elements. 2 elements if A is X, and 4 elements if A is different from X. It will be 4 elements, these 4 elements. Alright, so continuing, we can make some other examples. I can write another example for you here. Example 4. So let's say X is the real line, and then we have a set that is composed of intervals. Let's say it's a set of finite unions of intervals like this. AV open, close here and open here, A and this, and like this. So you have a set that is finite unions of these intervals, then of all of these combinations for every A and V. Then the set A is an algebra of R, but this is not a sigma algebra. And why this is not a sigma algebra? Well, because countable, well, it fails for the countable union of elements of A. To give a quick example, let's say that you have, this is a real line, and you have the first interval here that is 1 and 2, and then the other interval is 3 and 4, and so on, in this fashion. So the countable union of these will be this infinite set, unbounded and infinite, but this cannot be greater than like a finite union of intervals. Obviously cannot be. So these countable unions are not necessarily in A. Of course, some of the countable unions will be in A. For instance, if you have another example, 1 and 2, and then the other one is 2 and 3 like this, and the other one is closed, open, 3 and 4, and you have this countable infinite union, then everything this is this union will be equal to the set here that is of course an element of the algebra. Some infinite unions are included in A, but some others like this one are not included in A. So this makes this an algebra but not a sigma algebra. So this is it for the examples. Now let's go with a proposition. Proposition 2. So you have a measurable space X and A, measurable space, then it holds some 5 properties. And the first property is that the empty set is in the sigma algebra, and we have already proved here this, so we won't prove it again. The second property is that if you have an element, then its complement is in the sigma algebra. We have also proved this here because of this, right? X is an element of the sigma algebra, then difference are always in the sigma algebra, so the complement is in the sigma algebra, so it's pretty easy. And then intersections are maintained in the sigma algebra. We will prove this, and of course the following also holds. The symmetric difference, which is this, is also inside the sigma algebra, and moreover if you have a countable family, then the infinite intersection is an element. So we will work this. This is kind of easy to do. So let's make it quick. The intersection of, let's do it with a graph. So we have A, we have B, and we want to show that the intersection is always in the algebra. So what happens if you we know that difference by definition, this is our definition, this one here, the space is here and the difference is here, and countable unions and finite unions, we have proved this. So we will work with this. So this should be the difference of A and B, or some composition of A and B, and so on. So what happens if we make this? You know that this is the complement of B, which is an element of the algebra. So what happens when you make the difference between A and this complement? I mean, this difference. Well, then this difference will be equal to this intersection, because it is clear, I mean, with the drawing, right? Because the complement always it's shading this other part of A. So the only part that doesn't shade is the intersection here, and so this is an element of the sigma algebra, because complements are maintained in the algebra. So this is it. Then for the fourth property, you know the difference by definition are always in the algebra. Finite unions are always in the algebra also, because sigma algebras are algebras. Then this is in the algebra, so this is hold. And for the last property, if a family is in the algebra, then we can write some other family here. And this will also be a family in the algebra because for each element its complement is in the algebra. So by the third property of sigma-algebras, its countable union will be in the algebra, but then this is equal to the intersection like this. This is a property of sets. So this is an element of the algebra, but then complements are in the algebra. So the complement of the complement is just this intersection, which will be in the sigma algebra. So this is how we prove these three properties. So this will be it for today. If you have any questions, you can write it down in the comments below, and let's see you around.